Hello dear friends, welcome to BYJU'S Exam Prep and I welcome all for this particular Formula 1 series. Okay, and in this series today we are going to talk about algorithms formulae in one shot. Okay, see the main concentration would be the first part, that is beginning part, where we try to understand the mathematics of it properly, where most of the students are having trouble. Okay, hope you all able to hear me. Any doubts? All of you can hear me. Dear friends, still not back from Diwali, enjoying Diwali sessions or Diwali vacations. Hello dear friends, welcome back. In this formula series, today we are going to talk about algorithms formulae. And this is about me, myself, Sridhar Sir. I'm having 20 plus years of teaching experience and I'm associated with BYJU'S from past 1.5 years. We are working on this particular project called Recorded Gate Content, first of its kind, and we created visualized animated content for you. And under BYJU'S Exam Prep app, the category name is Learn with Video Lessons. You can find all these videos or the subjects which are recorded by me: engineering mathematics, discrete mathematics, algorithms, C programming and data structures, my dear friends. Okay, so now let us start with the story of today, that is Formula 1 series for the topic algorithms. Good evening Ashwini. Very good evening sir. So the study of algorithms mainly deals with the following things like designing of an algorithm. So where we discuss different or design strategies like divide and conquer, greedy, dynamic programming, etc. And how you express an algorithm. Of course, once you learn programming, you can express it in a programming language, but generally we use the high level description of the algorithm, which is called pseudocode, my dear friends. Correctness of the algorithm is one of the important concepts which requires the mathematical rigor, but generally in the beginning courses we generally avoid this verification or correctness of the algorithms, my dear friends. Okay, correctness is also one of the, or validating algorithm is also one of the important areas of work under algorithms. Analyzing algorithm, how long or how much time and space the algorithm is going to take, that also we are going to discuss under analysis of algorithm. And again, this analysis of algorithms are into two parts. One is called a priori analysis, the other one is posterior analysis. And we are interested in this priori analysis, where we are not interested in a particular program, but we are interested in a high level description and we need a machine independent analysis, my dear friends. Okay, so that is what we are going to do most of the time. And implementation, of course, once you write a beautiful algorithm and you analyze how long it takes, okay, before actually executing, then you can implement it, then you can test, my dear friends. So study of algorithm involves all this, but mainly in undergraduate courses we study the design strategies, like different design strategies we are going to study, and how to express an algorithm we are going to study, and how to analyze an algorithm we are going to study. These are the three important areas which we are actually going to learn under algorithms course in any of our undergraduate studies, my dear friends. Am I clear? Now there are some mathematical prelims which we should know. Most of the people are having trouble with it, so I thought, like, first let me start with some basic mathematical formulae which we need to know. A inverse is 1 by a power m whole power n is a power mn, and a power m into a power n is bases are same, powers are added. So these are all some basic formulae, but majority of the time you will be using them in your algorithm, especially when you are finding complexities, my dear friends. Then this is one important limit formula which you are going to use. Limit as n approaching infinity, 1 plus x by n whole power n is e power x, my dear friends. Okay, so these are some exponential formulae. Then logarithm plays very important role. Hi Vijender, very good evening sir. Okay, see, when x is log a, what do you mean by that? Actually, when a is b power x, this actually means that x will be log a to the base b. So log a to the base b is x, means what, sir? A is equal to b power x. Am I clear? So the natural logarithm is denoted by ln a, which is log a to the base e, whereas binary logarithm is log a, LGA we write it, which is log of a to the base 2. And in algorithm course, we are mainly interested in logarithmic base 2. That is binary logarithms we are mostly interested in. Generally, unless or otherwise explicitly mentioned, whenever you say log, we mean binary logarithm under algorithm course, my dear friends. Whereas in engineering mathematics, whenever you say log, a log of something, we mean log to the base e, natural logarithm. But in algorithm course, we are interested in the binary logarithms, my dear friends. Very good evening and good evening, sir. Some properties, important properties of the logarithm, and I'll give you one very important formula which we regularly use while using algorithms, my dear friends. Log AB. Log AB is log A plus log B. Whereas log A power n is n log E. See, this formula we come across many times, my dear friends. Because one of the important formula when you compare functions, this logarithmic formula plays very, very important role. So logarithmic formulas you should know. If you do not know, I am giving them in an orderly manner. Please note it and practice. Don't practice just like this. You can practice like, log 2 cube is nothing but 3 log 2. Like that you can practice, sir. With some numbers you can practice, my dear friends. Am I clear? Log 1 by a. Suppose you want to write 1 by a as a by 1. Then what happens when you reverse this? What happens? You get minus log a, my dear friends. Minus log a to the base b. And log a by b is nothing but log a minus log b. And log a to the base b, if you want to exchange the value and the base, you can just divide by 1, sir. 1 by log b to the base a, my dear friends. Actually, this formula plays very, very important role, my dear friends. See, generally when you solve problems, you get something like log n to the base 5. And they write it as log n, that is log to the base 2 they write it. And how can you write like that, my dear friends? Because of this formula. Of course, it's not exactly, it is approximation. See, the idea is when you have log n to the base 5, according to this formula, you can write it as log n to the base 2 and log 2 to the base 5. Means what? The log n to the base 5 can be written as log n to the base 2 multiplied with log 2 to the base 5. See, log 2 to the base 5 is just a constant, whereas it is natural logarithm, my dear friends. So, log n to the base 5 is actually some constant times log n. And the coefficients can be ignored because they are machine independent or machine dependent constants. So, generally we ignore, my dear friends. Namaste, sir. Good evening, Nitya. Very good evening, sir. Am I clear? So, because of that, what we generally say, the base of logarithm does not matter. And this is the formula which actually helps you in understanding that the base of logarithm does not matter. Because hardly when you change the base of logarithm, it is equivalent to multiplying with a constant, my dear friends. And this is one of the important formula. We generally come across this many times, my dear friends. We generally come across this many times. For example, you are having like 2 power n log 2. What is the complexity, they ask? So according to this, what happens? You can swap this a and c, my dear friends. A and c can be swapped. So what happens? It is c power log a to the base b. So what happens? This 2 and n will be swapped. So it is n power log 2 to the base 2. What is log 2 to the base 2? Log a to the base a is 1. Okay? Therefore it is becoming n. So this problem is exactly same as theta n complexity, my dear friends. Many times in algorithms, when comparing functions, this type of problems will come where this logarithmic prelims will help you a lot. So I just giving the important logarithmic formula which we need to know, and it is more than enough for you, my dear friends. If you know this, it is sufficient for your GATE examination. And a is equal to b power log a to the base b. Because here what happens, this a and b can be swapped. A and b can be swapped. So what happens, it is a power log b to the base b. Log b to the base b is 1. So you get a power 1, which is a. So whenever you have any n, this can be written as some constant. See this n, suppose if it is n, you can write some constant b log n to the base b. See, this b log b cancels and you are going to get n. See, generally what people do, they cancel and they write n directly because of this. And log square a means log a whole square, my dear friends. There is a difference between log square a and log a square. These two are not same. Please note this point, my dear friends. Log square a is log a whole square, whereas log a square is 2 log a. So they are not same. Please note that point. That is very, very important, my dear friends. C power log C to the base n. Yes. What happens? C power log C to the base n. What happens in this? Okay. See, what you can do is nothing much can be done for this, my dear friends. Because if you want, what can be done? This C and C cannot be interchanged. That will be the same, my dear friends. Okay. That will be the same. So what you do with that? That will be the same. Am I clear? And log A is nothing but log of log E. Okay, please note that. And as I told you, base of logarithm does not matter. Base of logarithm does not matter. So whenever you have log A to the base B, some answer, many times you get complexity like log A to some constant B, that will be changed to, generally the C is actually 2. Am I clear? So you get log A to the base B, that will be written as log A to the base 2 into log 2 to the base some constant, my dear friends, which is B. So in this particular case, what happened? This would be constant, and it is log A to the base 2 will be log A. That is LGA, binary logarithm, my dear friends. That would be binary logarithm, my dear friends. Some constant times. Some constant times. Is the idea clear? But power matters. You cannot change. For example, if you are having 2 power n, you cannot change it as 3 power n, sir. It matters. It matters. Because 2 power n, if you want to change it as 5 power n, you have to multiply with 2 by 5 whole power n, which is not a constant. This is not a constant. So what is the point to be noted? Base of logarithm matters, but, base of logarithm does not matter, but base of exponent matters. Base of exponent matters, but base of logarithm does not matter, my dear friends. That you can do, sir. That you can do. That will be n, my dear friends. That will be n. Vijayendra. That would be n. Yes. There are some general arithmetic sequences which we need to know. So this is what you call it as arithmetic progression or arithmetic sequence, where every time you are adding common difference d like that. So here nth term is given by a plus n minus 1 into d, and sum to n terms is given by n by 2 into 2a plus n minus 1 into d, whereas this can be written as n by 2 into a plus n minus 1 into d, which is your nth term. So nth term is also written as last term. So this sometimes people also write as n by 2 plus t1. t1 is first term plus tn. tn is nth term, my dear friends. So this is the formula for arithmetic sequence, my dear friends. Similarly, geometric sequence also plays very important role. The nth term of a geometric sequence or geometric progression is given by a into r power n minus 1, and sum to n terms of a geometric progression is given by a into r power n minus 1 by r minus 1 if r is greater than 1. And if r is less than 1, it is a into 1 minus r power n by 1 minus r, my dear friends. One more interesting formula which I generally ask: when r is equal to 1, what is the story? When r is 1, what is the story? What is the story when r is 1, my dear friends? Please answer. Is my audio clear to you all? All of you able to hear me carefully or properly? See, r is equal to 1, it is not 0, Vijayendra. It is actually because a added to itself n times, you are going to get na, my dear friends. It is na, it is not 0. See, I am not talking about sum to infinite terms. I am talking about sum to n terms. Vijayendra, I am talking about sum to n terms, not sum to infinite terms. The sum to infinite term formula is possible only when r value lies between minus 1 to plus 1. R value lies between minus 1 to plus 1, my dear friends. It lies between minus 1 to plus 1. And it is a by 1 minus r, provided the value of r is a fraction, negative or positive fraction lying between minus 1 to plus 1. It can be 0 also, my dear friends. Some more important series. It is same as your geometric progression formula only, my dear friends. Sigma 1 plus x, okay, where x is not equal to 1, and we are assuming that x is greater than 1. It is x power n plus 1 minus 1 by x minus 1. And this is mod x is less than 1. That is, it is lying between minus 1 to plus 1. Sum to infinite terms is given by 1 by 1 minus x, which is exactly same as your geometric series sum to infinite terms, my dear friends. some more important series, constant series. If you add 1 to itself n times, you are going to get, okay, b minus a plus 1, b minus a plus 1. For example, if you are going from 1 to n constant, what happens? 1 is added to itself n times and you write it as theta n, my dear friends. The complexity would be theta n. Now here, sum of first n natural numbers. See, most of the time the time complexities will be turned out to be this sum of first n natural numbers, which is nothing but n into n plus 1 by 2. See, what happens here is we write it as half into n square plus n by 2, or half n. So here what happens, the order of growth notation, I will be describing that in a little later. The lower order terms are dropped and we ignore the coefficient of highest order term, and we can write it as theta n square, my dear friends. We can write it as theta n square. Yes, yes. And similarly, quadratic series, sum of squares of first n natural numbers, ignoring lower order terms and dropping the coefficient of highest order term, this can be written as theta n cube, my dear friends. And similarly, sum of cubes of first n natural numbers is n square plus n plus 1 whole square divided by 4, which is nothing but theta n power 4, my dear friends. Which is theta n power 4, my dear friends. Very good, Vijayendra. Super. And we can also go for biquadratic series, sir. Mostly this formula may not be available everywhere, but you can just take for completeness. So it would be of order what, sir? N square, n cube, n power 5. It is of order n power 5. We only have access up to biquadratic series, that is sum of fourth powers of n numbers, first n natural numbers, and in general sum of pth powers of first n natural numbers, 1 power p plus 2 power p and so on, n power p is approximately equal to, that is, it's not exact answer, but it is approximately equal to n power p plus 1 by p plus 1, my dear friends. So it is, because we do not know exact answer, so because it is an approximate answer, instead of taking theta notation, we take big O notation for this. See, my dear friends, big O notation is always safe notation. Big O notation is always safe notation, my dear friends. So whenever you find sum of cubes, sum of power 4, sum of power 5s and so on, we can write plus 1, my dear friend. Order n power p plus 1. You can say always order n plus p plus 1. What is constant time 1? Yeah, see, this is constant time, sir. Theta 1 we denote it as constant time. This is called linear time. This is called linear time. This is called log. Okay, logarithmic time. Okay, so we can also have, polynomial. N power k is poly. And we can also have log n power k or log power kn, which is called polylog. Like that we can have many other names, my dear friends. Different complexities can be there. Different complexities can be there. And one more important series is this harmonic series. Actually, this 1 plus 1 by 2 plus 1 by 3 and so on, 1 by n, it is approximated because it is a summation. Okay, the summation is approximated with integration. We get 1 by x dx, where x vary from 1 to n, and 1 by x integral is log x, where limits are from 1 to n, my dear friends. Log n minus log 1 is 0. And as I told you, base of logarithm does not matter. So it is approximated with log n to the base 2, my dear friends. So this is approximated with log n to the base 2, my dear friends. So because of that, we generally write for harmonic series, the time complexity is theta log n to the base 2. Even though it is log n to the base e, the base of logarithm does not matter. Therefore, we express this as theta log n, my dear friends. Yes. Very good, Nitya. Very, very super. Now there is one very important approximation for this n factorial, which is called Stirling's approximation. And that is given by n factorial is equal to root 2 pi n into n by e whole power n plus 1 plus theta of 1 by n, sir. So when you see this particular one, am I clear? It is root 2 pi into root n, that is n power half, n power n by e power n, my dear friends. Actually, when you apply log on both sides, we can easily understand that this can be approximated with, the log n factorial can be approximated with theta n log n, my dear friends. It is approximated with theta n log n. And this n factorial would be larger than 2 power n, but would be smaller than n power n, my dear friends. So because of that, we can say that, okay, n factorial is having n power n as upper bound and 2 power n as the lower bound, my dear friends. Because of this, n factorial is having n power n as the upper bound, whereas 2 power n as the lower bound, asymptotic lower bound, my dear friends. Am I clear? Of course, this is not normal less than, sir. It is less than in the sense asymptotically smaller. 2 power n is asymptotically smaller than n factorial is asymptotically smaller than n power. Now I'll give you wonderful results, my dear friends. Of course, because before that there is one wonderful result, which is sigma k is equal to 1 to n. Log k means what, sir? Log 1 plus log 2 plus log 3 and so on, log n, which is nothing but log 1 into 2 into 3 into and so on n, which is nothing but log n factorial. And log n factorial is theta n log. Is theta n log. So that is the answer, my dear friends. So sigma log k is log theta n log n, my dear friend. Not just log n, theta n log n, my dear friends. Now we all know the big O notation. Big O notation tells you that asymptotic tight upper bound. Asymptotic tight upper bound. And when you say Fn is big O of Gn, my dear friends, the meaning of this is Fn is less than or equal to some constant times Gn for one C and one N naught. After N naught, that Fn will be smaller or equal to C times Gn, my dear friends. So suppose this is your Fn, this is your C times Gn. Now you see, this is your N naught. Before N naught, sometimes F may be larger, sometimes C times Gn may be larger. But after N naught, C times Gn is always larger than Fn. Okay? So Fn has order of growth less than or equal to C times Gn, or Fn grows no faster than Gn, we say. See, actually, Fn is less than or equal to constant times Gn. But when you say asymptotically, that constant we don't mention. We simply say that Fn is having Gn as its asymptotic upper bound. We simply say that Gn is asymptotic upper bound for Fn. Gn is asymptotically. Asymptotic, don't worry about that term, sir. Asymptotic means for large values of n, nothing more than that. See, that is all cat law numbers, sir. Amit Sharma, they are all, cat law numbers formulae that are, okay. Big omega notation. Fn is big omega, Gn means what? Means what, sir? Fn is big omega means Gn is here asymptotic tight lower bound. Gn is asymptotic tight lower bound. That is constant times Gn is less than or equal to Fn, my dear friends. So this is Fn. See, after this N naught, always C times Gn is smaller than Fn, my dear friends. After C times Gn, that is after N naught, the C times Gn is smaller or equal to Fn, my dear friends. Yeah. See, generally this is a wrong understanding, like, big O means worst case, big omega means best case, big theta means average case. That is wrong understanding. There is nothing like that, my dear friends. There is nothing like that. See, for any function, we can have big O notation, we can have big omega notation, we can have big theta notation. That is, even for worst case, we can have big theta notation, big O notation, big omega notation. Average case also, we can have big O, big theta, big omega, my dear friends. Even for the best case, we can have big O, big theta, big omega. There is nothing like, average means big theta. This is wrong understanding. Please don't do that. Am I clear? Nitya, that is wrong understanding. Okay? Best case is the least time taken over all the complexities of that particular function. Okay, it is the least of all possible times. Am I clear? For all possible inputs. Like that. Yes. Theta means what? It's a asymptotic tight bound. That is, after N naught, some constant time Gn is smaller than or equal to Fn is smaller than or equal to some constant times Fn. That is, this Fn will be sandwiched between C times G1 or C1 times G1 and C2 times Gn, my dear friends. And small o notation is, it is strictly upper bound, cannot be equal to. So here we say that Fn is asymptotically smaller than Gn. Fn is asymptotically smaller than Gn. Here when you say big O notation, we should be able to find at least one C. But here this must be satisfied for every C, sir. This must be satisfied for every C. That is the difference between big O and small o notation, my dear friends. See, verifying for one C is very simple, but verifying for every C is very difficult. Generally, for that purpose, we generally use the limit formula, which I am going to give you. So here what happens, this C times Gn should be larger than Fn for all C, my dear friend, for all C, not one C, sir. You multiply with any C, that any positive C, that should be larger than Fn, my dear friend. Fn should be smaller than C times Gn, my dear friends. See, big O notation is asymptotic tight upper bound, whereas small o notation is just asymptotic upper bound, not tight, which is not tight. It is asymptotic upper bound, which is not tight. And small omega notation is, it is asymptotic lower bound, which need not be tight, my dear friends. Okay. So C times Gn is less than Fn for all n greater than or equal to n naught, whereas this C is not a single C. You have to prove it for every C. But verification for every C is very difficult. So what we do is, we generally use this limit formula, my dear friend. This is the most important formula which helps you in solving many problems, my dear friends. Which helps you in solving many problems. So you take limit as n approaching infinity Fn by Gn. You get some limit value A. Suppose if A is 0 means, if A is 0 means what, sir? The limit is 0 means what? The denominator is larger. The denominator is larger. In that particular case, Fn is small o. Fn is small o of Gn, my dear friends. We can conclude Fn is small o of Gn. Suppose if A tends to infinity means numerator is larger. That is, Fn is small omega of Gn. That is, Fn is larger than Gn, my dear friends. Suppose if the limit is a finite non-zero value, then Fn and Gn have equal order of growth, my dear friends. Fn and Gn have equal order of growth, my dear friends. Am I clear? So this limit formula helps you in solving problems very, very quickly. See, later on we try to understand, whenever it is small o, that is, small o means what, sir? Fn is asymptotically, okay, let me do it here itself. What do you mean by Fn is small o, sir? Fn is small o means Fn is asymptotically smaller than Gn. Whenever it is asymptotically smaller, we can say that it is asymptotically smaller or equal, you can say. That is, whenever Fn is small o of Gn, we can happily say that Fn is big O of Gn. So we can use this limit formula for big O also without any trouble. So whenever it is small o of Gn, we can happily announce that it is big O of Gn. But whenever it is big O, we cannot say small o, sir. Please remember, the reverse is not true. Only in this direction it is true, sir. Similarly, Fn is small omega. Whenever it happens, we can say big omega of Gn, but not vice versa. Not vice versa. Reverse is not possible, my dear friends. Of course, later on, when I discuss the properties, I will give you that property also. Okay? Like. See, properties of exam, these properties they ask you in examination directly, sir, and most of the people are having difficulty in writing these properties in orderly manner, understanding these limit formulas also, so I just giving that. Okay? Right. And one thing which we need to understand is, when you say Fn is big O of Gn means F is asymptotically smaller or equal to G. See here, this is asymptotic, sir, not regular less than or equal to, we need to understand. So when you say this means Fn should be less than or equal to some constant times Gn. Fn should be less than or equal to some constant times Gn, you need to understand. Okay? Yeah. Similarly, Fn is big omega of Gn is F is asymptotically larger than G, and Fn is theta means they are of equal order of growth, my dear friends. And Fn is small o means it is asymptotically smaller but not equal, and small omega means it is larger but not equal. And generally, when you have two functions, it is not necessary that they must be related in some way. You can have functions which are nowhere related, my dear friends. For example, you take these two functions, it's a very famous example where these are not related, my dear friend. These two functions are not related with each other. Okay? because as n approaching infinity, this n power 1 plus sine n, because sine n value can be varying from what, sir? Minus 1 to plus 1. When it is minus 1, it tends to n power 0. When it is plus 1, it varies to n square. So its value is n power 0 to n square, it is varying. So you cannot compare that with n. So you cannot compare two functions also. It may also happen that two functions are not comparable. There is no trichotomy. See, if you have two numbers, either it should be less than, or it should be greater than, or it should be equal. But this does not happen for the functions, my dear friends. That you need to note. हाँ नहीं मिलेगा, अटेंड करे तो ही मिलेगा, नहीं तो नहीं मिलेगा. Now I give you the most important properties. These are the direct gate questions, my dear friends. See, the reflexive property is satisfied by these fellows: theta, big omega, and big O. That is, every function is big O of itself, big omega itself, big theta of itself. So this is satisfied by theta, big omega, and big O, my dear friends. But it is not satisfied by small o and small g, because you cannot say f is smaller than f or f is larger than f. Can you say that? We can't say that. Similarly, symmetry is satisfied only for theta, sir. It is satisfied only for theta. If fn is big theta of gn, then gn is big theta of fn. But you cannot do it for big O, big omega, small o, small omega, my dear friends. Transitivity. Transitivity property means if fn is big theta of gn, then gn is big theta of, transitive means A related to B, B related to C, then A related to C. That is the transitive property. Suppose fn is big theta of gn, gn is big theta of hn, then first function is big theta of last function. And this transitivity property is satisfied by big theta, big O, big omega, small o, small omega, my dear friends. All these fellows satisfy this transitive property, my dear friends. All these fellows satisfy transitive property, the most important property. See, this type of question they'll ask you, which of the following property is satisfied by small o? Okay, symmetry, okay, reflexivity, transitivity, none. So you can say transitivity is satisfied by small o. Small o only satisfies transitivity, but it does not satisfy reflexivity, it does not satisfy symmetry, my dear friends. See, the transpose symmetry is satisfied by only big O, big omega, and small o, small omega. Suppose fn is big O of gn, then gn is big omega of fn. That is simple, sir. If fn is less than or equal to gn, then what happens? Gn is greater than or equal to fn. Similarly, if fn is smaller than gn, then gn is larger than fn. So that is the simple logic, my dear friends, for these properties. And as I told you, whenever fn is small o of gn, that is, whenever f is asymptotically smaller than g, see, when it is smaller, you can say smaller or equal without any trouble. Similarly, whenever f is asymptotically larger than g, we can say larger or equal to g, but not vice versa. That is, the converse need not be true, my dear friends. So this is the idea, my dear friends. Yes, transpose symmetry, I think I already given that. This is a transpose symmetry possible only for big O and small o. That is, big O, big omega, small o and small omega only. Not satisfied for theta and theta notation, my dear friends. हाँ, equal नहीं होता है. That is asymptotically smaller. Asymptotically smaller. Okay. For example, n square and n power 2.1. Here you can say n square is asymptotically smaller than n power 2.1. Now you consider 2n square and 3n square plus 4n plus 5. Now here you cannot say this is asymptotically smaller than this. It is wrong. Because they are actually asymptotically equal. They cannot be less than, my dear friends. See, whenever you say something is asymptotically smaller, means the power must be at least a part of that must be less than that. That is, it should be 2 minus n power 2 minus some 0.0000001 also you can do it. Okay, then only it is smaller, my dear friends. This is what I already told you. Fn is smaller means it is less than or equal to, you can say, but less than or equal to you cannot say smaller, my dear friends. Reverse is not. And this is one very important result, order of growth. See, whenever you are having a function written as sum of many functions, and if all these fellows are having lower order growth than f1, that is f1 is smaller than, larger than f2, f1 is larger than f3, and so on, fn is larger than fn. So all these are called lower order terms. You can cancel them. The lower order terms can be cancelled, my dear friend, because their effect would be negligible, my dear friends. Asymptotically, their effect would be negligible. So you can simply write fn is theta of f1n. This is the basic idea of order of growth notation. That's why whenever you are having something like, you get answer like 2n square plus 4n plus 5, you simply ignore these fellows or drop these fellows and you write it is theta of 2n square. Then later on with the next result, this constant factor also we can ignore it because that is a machine dependent constant, my dear friends. So that is also ignored. This constant also can be ignored. So what happens ultimately, suppose you got 2n square plus 4n plus 5. This lower order terms are cancelled because of the previous result and this coefficient is ignored because of this result, my dear friends. So you can happily write it as theta n square, my dear friends. You can happily write it as theta n square. Is the idea clear? So this is what we call it as order of growth. It is another abstraction to ease our analysis, my dear friends, for writing time complexities. And because of this, suppose you are having any polynomial, just now I told you, the lower order terms can be cancelled and just should be am into n power m. Even this coefficient can be ignored, therefore fn is theta of n power m. So whenever you have any polynomial, drop all lower order terms or ignore all the lower order terms, then ignore the coefficient of highest order term, my dear friend. So directly n power, whatever highest power is there, that would be your answer. That is because of this order of growth notation. And this is one more important result, sir. Suppose T1 is big O of F1, Fn, and T2 is also big O of Gn. The product would be, see, it's like, one is n square, one is n cube. The product would be obviously n power 5. So that's it. Just multiply them. F1, Fn into Gn, my dear friends. So T1 into T2 would be big O of F into G, my dear friends. If it is theta, then same story. T1 into T2 is big theta of F into G. If it is big omega, then T1 into T2 is big omega of F into G, my dear friends. But the most interesting result is this. This is a very important result and most of the time it helps you a lot. And if you know T1 is big O of Fn and T2 is big O of Gn, T1 plus T2. See, it's like this. For example, it is say n square plus 3n plus 5 and it is say 3n cube plus 4n plus 5 or 4n square plus 5n plus 6. When you add these two fellows, highest order term would be n cube. So all the lower order terms will be cancelled, my dear friends. So whatever is maximum, that will come into play. So T1 plus T2 is big O of maximum of these two fellows, my dear friends. Maximum of Fn, Gn, my dear friends. Same is the case with big theta and same is the case with big omega, my dear friends. Yes, Nishu. Yes, Niche. See, transpose symmetry is for big O, big omega, small omega. Transpose symmetry, Nitya, Nishu, I don't know which one you are asking about, that small O, small omega. Yeah, these are not for small O and small omega. These results only for big O, big theta and big omega, not for small O, small omega, my dear friends. We can't say exactly for that. Again, we need to see what is that particular function. It may depend on that particular, my dear friends. Am I clear? Yes or no? Because when you say small o, there will be some confusion. So we can't exactly say. Yeah. Now this is the most important ordering, dominance ranking, you can say. Most of the problems in your GATE exam can be handled if you know this dominance ranking, my dear friends. Most of the problems can be easily answered. Recently I taken one session for most of the people where I solved the problems and most of the people felt that very simple. The problems are very simple just because of this. It's available under your BYJU'S Exam Prep app, free classes. where I taken this asymptotic notation. One day I taken the concept, one day I taken the PYQs, sir. I solved all the PYQs within no time just because of this result, my dear friends. This result, if you understand, most of the problems can be handled within no time, my dear friends. So log n power a, this is called polylog, is asymptotically smaller than n power b, is asymptotically smaller than c power n, is asymptotically smaller than n factorial, is asymptotically smaller than n power n, is asymptotically smaller than 2 power n, my dear friends. This is the most important ordering, my dear friends. And this is the most important basic dominance ranking, my dear friends. 1 is less than log n. Log n is smaller than, see this log n is like log n power 1 and this is n power half. Not only that, you take log n power 100, my dear friends. You take log n power 100 and you take n power half. Still this is valid, my dear friends, because you have log n power a is asymptotically smaller than n power b. See, it may not happen for small values of n. See, when you talk about this asymptotic notation means for large values of n you are talking about. You are not talking about small values of n, my dear friends. So please note that point, my dear friends. And this is the most important dominance ranking. See, most of the problems can be handled if you know this basic dominance ranking, my dear friends. Of course, in place of n, if you put log n, so it is log n is smaller than root log n is smaller than log n is smaller than log n into log n power half, that is log n power 3 by 2 is less than log n whole square is less than log n whole cube, 2 power log n. Just now I told you 2 log n, these two can be exchanged, so you get n power log 2. So this is log 2 is 1, so you get n. So it is smaller than n. And log n factorial, this is log n whole factorial, not log n factorial, sir. It is log n whole factorial, n factorial, like log n whole factorial. So this dominance ranking you can create if you know the basic dominance ranking, my dear friend. So what I am going to give you some advanced dominance ranking also. 1 is smaller than log n, which is smaller than root log n, which is smaller than log n, which is smaller than log square n, which is smaller than, that is any log power is smaller than n power something, sir. Maybe root n, and root n is smaller than n, okay, and n is smaller than log n factorial. See, log n whole factorial is different from log n factorial. This is log n factorial because log n factorial, by Stirling's approximation you get this result, sir, theta n log n. This is the most important result, my dear friends. The most important result. One should know. Am I clear? So this is the most important dominance ranking which we should know, my dear friends. And most of the problems are handled with this beautiful result, my dear friends. Most of the problems are handled with this beautiful result, my dear friends. See, for example, once they asked n root n and n factorial, which one is larger? N power root n and n factorial, which one is larger? Okay, so according to this result, what it says, suppose if log phi n is small o, that is log phi n is asymptotically smaller than log psi n, in that particular case only we can say phi n is smaller than psi n. See, if you don't like phi and psi, you can replace with f and g, sir. Log f is smaller than log g, then f is smaller than g. That is the result, my dear friends. And this result we can use for solving many problems. But it is not reverse, sir. It is not reverse. This is only in this direction it is correct. In the reverse it is not correct. Suppose for f is smaller than g, you cannot say log f is smaller than log g, you cannot say, sir. If log f is smaller than log g, you can say f is smaller than g, but f is smaller than g, you cannot say. Reverse is not correct, sir. Reverse is not correct, please note it. So here you can say log n root n, and it is log n factorial, my dear friends. So this is root n log n, whereas log n factorial is what, sir? Log n factorial is n log n. Out of these two, which one is smaller? This is smaller. That is, log of this is smaller than this means n power root n is smaller than n factorial, my dear friends. So you can solve such problems very easily if you know such basic and important results, my dear friends. Now comes time complexity, performance evaluation we call it. See, the time complexity of an algorithm is the amount of computing time or processing time taken by an algorithm to run to completion. whereas space complexity is the amount of memory taken by an algorithm to run to completion. See, most of the time we talk about time complexity because there are many articles, results which are based on time complexity available than space complexity. And one more reason why we don't much talk about this space complexity is the space can be reused or it can be extended, but that is not possible with time. Because of that, most of the time we talk about time complexity only. But space complexity, of course, we talk whenever you talk about recursion, my dear friends. Because whenever you are using recursion, what happens? There will be recursion stack taking place. So we should talk about space complexity whenever you are using the recursive algorithms, my dear friends. Yes, Nitya, you are writing things in a very simplified manner. But finding exact runtime or time complexity is very complex because it depends on many things like, the machine which you are using, or the programming language you are using, or the many machine dependent things like, processor which you are using, architecture. That it depends on many things. So we should create the approximation for this time complexity as machine independent as possible. It should be using only high level description like pseudocode only, and it should be machine independent. So what we use is, we use the notion of step or statement count. That is how many times or how many statements are executed. We are interested in that. Now, this number of statement executed is the measure for our time complexity, is an estimate for our time complexity, my dear friend. It is like number of statements. But it is not like single statement, no, there can be many statements. So, cost of the statement into number of times the statement is executed. So, we are going to do it over all the statements. We are going to do it over all the statements, my dear friends. But sometimes, some statements may be repeated based on your input. Based on your input, what happens? Some statement may be repeated, my dear friends. So, ultimately what happens? You can express the time complexity as a function of input size. So here basic problems, our input size will be is characterized by single parameter, like our sorting algorithms, they are all characterized by single parameters like size of array, like that. But it's not necessary that input size is characterized by single parameters. Input size also can be characterized by multi parameters. For example, graph algorithms, when you see, if you use the adjacency list representation, we may use multi parameters. Okay, like number of vertices as well as number of edges will be the parameters, my dear friends. But whatever it may be, we can estimate time complexity as a function of input size, because based on the input size, some statements may be repeated, my dear friends. Am I clear? So ultimately time complexity can be estimated as function of input size, my dear friends. Yes, Nitya. I like the way Nitya is, writing the statements which I am saying in a very simple manner. Might be she is correcting me, I don't know. Right? Now, suppose if you are having a single statement, for example, x is equal to 10 plus y. Such single statement, the cost may be some constant. How many times it is executed? One time it's executed. Now, suppose you may be having consecutive statements. Suppose you may be having consecutive statements like, y is 10, z is 20, and x is equal to y plus z. So this also may take constant time. Each fellow is executing one time, my dear friends. See, when I am talking about a particular result, you are asking about DFT algorithm. You are talking about, what do you call depth first tree, what you call it. That is what you are talking about. It depends on for what purpose you are doing. Suppose if they ask you to find the best route or tree, bind or spanning tree for a algorithm or for a particular connected graph, you use BFT or DFT, does not matter, my dear friends. But if it is a different story where he is interested in a DFT construction, in such cases all that will be important. It depends on the type of question, my dear friends. Whether it is important or not, it depends on, because there are so many graph based questions which were asked in GATE examination, and for all those things these ideas are useful, my dear friends. Am I clear? That's very important. And suppose if you are having selection statements, so you may be having some if condition, then we have if block, otherwise else block. So the time complexity for this is, it depends on, you know, the if condition plus maximum of if or else block. See, if block may be having one statement, but else block may be having 10 statements. In that, 10 is highest. Suppose if block is having 20 statement, else block is having 5 statement, then 20 is highest. So the time complexity is considered by this particular formula, my dear friends. But what what generally contributes more to your time complexity is the loops. Okay, the selection structures, of course, they may contribute, but what actually contribute more to your time complexity, generally makes your time complexity as function of input size, is the repetition structures, the loop structures. Okay, so whenever you are having loop, how many iterations are there in, that is how many times the loop is iterating and how many statements are inside the loop, that will be the time complexity, my dear friends. And most of the time, the number of iterations of the loop will depend on the size of input. Because of that, ultimately the time complexity would be a function of input size, my dear friends. Suppose if time complexity does not depend on input size, time complexity would be constant only, my dear friends. Now, as I told you earlier also, I told you, lower order powers you can cancel out because their effect would be negligible, and coefficient of highest order term can be ignored because it is a machine dependent constant. So for example, if you are having 2n square plus 3n plus 5, we already given this with a formula also or result also. The lower order terms are dropped and ignore the coefficient of highest order terms, and suppose your time complexity is this, we can simply write it as theta n square. See, time complexity itself is an estimation. We are not finding exact time complexity because finding exact time complexity is very, very difficult. Difficult in the sense it depends on many issues like, you know, types of inputs, machine dependent issues, type of computer you are using, what programming language you are using. It depends on many things, my dear friends. Processor, architecture, like that, many things it depends. So we cannot estimate time complexity based on all these factors. So we try to analyze time factor or time complexity in such a way that it is as machine independent as follows. So generally we estimate time complexity as function of input size. That is an estimation. Now this is another estimation to ease our analysis. So where this particular estimation depends only on the factors which actually contributes to the time complexity, my dear friends. So we ignore the lower order terms because their effect would be negligible. We drop the coefficient of highest order term as it is a machine dependent constant, because we are interested in an estimation which is as time or not time, as machine independent as follows. So to express this, what we use is this asymptotic notation, my dear friends. So there are some loop structures. We should know readily what is the time complexity. Whenever you find this particular for loop, my dear friend, in your problem, for I is equal to 1, I less than or equal to n, and I is equal to I plus c. See, this c can be any constant as long as it is constant. For example, if I give you a problem like I is equal to 1, I less than or equal to n, I is equal to I plus 5, some statement I give you. You know what is the time complexity for this? Simply how many times it iterates, my dear friends? See, actually it may iterate n by 5 times, but coefficient of highest order term can be dropped, therefore it is n times, my dear friends. So whenever you are going from I is equal to 1 to n, okay, with increment of a small constant c, or from n to 1 with decrement of small constant c, the time complexity would be theta n, my dear friends. The time complexity would be theta n, my dear friends. The most important result, please remember. Is the idea clear? Now, suppose you are going from 1 to n in the multiples of c as long as c is constant, or you are going from n to 1 with multiples of 1 by c, or dividing by c, constant c, where c is a constant factor. The complexity would be theta log n, my dear friends. Okay, what would be the complexity? The complexity would be theta log n. Actually, theta log n to the base c, but base of logarithm does not matter, my dear friends. Therefore, you can write theta log n. And there is one more interesting result. You are going from, of course, here it is not from 1, sir, because you are raising to the power c, means if it is 1 power c, every time it would be 1 only. So please be careful. It may be 2 or anything else. It's not 1, anything other than 1, 2, 3, 4 or any constant. You are going to reach n with powers of c every time, or from n to constant other than 1, you are coming down with cube or cth root of that number every time. The complexity would be log n. Very good. The complexity would be log n. So these are the most important complexities one should know. Then what happens? They'll combine them in the form of nested loops. The nested loop may be independent nested loop. See here, the value of I and j does not depend on each other. This is called independent nested loop. In this case, here it iterates n times, it also iterates n times. So the time complexity is simply product of them. Theta n into n, that is theta n square, my dear friends. Wonderful, Vijayendra. Whereas dependent nested loop, what happens? In the dependent nested loop, what happens? The j value, here. The j value depends on I. That is, inner nested loop values dependent on outer nested loop, my dear friends. So actually, if you want to solve this, we use this sigma notation, summation notation. Sigma I is equal to 1 to n. Sigma j is equal to, I think it is I, no? Then it's fine. I to n. I is already there, no? Thought it is 1. I is there, no? So I to n. And every how many statements are executed like this? This will be solved like this, my dear friends. So if you simplify this, it is I is equal to 1 to n. And how many ones are? I to n. So you can say n minus I plus 1, my dear friends. Now you can use this summation notation for this. Sigma n is a constant with respect to I, sir. So sigma 1 is n. And it is sigma I is sum of first n natural numbers. That is n into n plus 1 by 2. And it is plus 1 sigma 1 is n. So it is n square, or you can take LCM also. 2 is the LCM, 2n square minus n square minus n minus 2. Plus 2n, my friends. Now what happens? This n square minus n plus 2n, that is plus n by 2. Whatever it is, the lower order terms can be cancelled, and ignore the coefficient of highest order terms. You are going to get theta n square, my dear friends. See, generally algorithms people find it difficult because of all this, sir. That's why I am concentrating more on this. See, the rest of the story is finding time complexities only. We just need to understand, the recurrence formulae. Because if you see divide and conquer recurrence or design strategy, that is entirely based on how to solve the recurrence relations. Of course, problem solving means how merge sort is done, how quick sort is done, how binary search is done. They are all problems only. But ultimately, for that particular problem, the time complexity turns out to be a recurrence relation. We should know how to solve recurrence relation. For dynamic programming, the recurrence relation will be there. Of course, we don't derive the complete time complexity for dynamic programming. In dynamic programming, what they ask, maybe problems they ask, generally most of the people, they never use the dynamic programming approach. They solve by normal approach only, the problems. See, if you solve by normal approach, what is the use of applying algorithm techniques, my dear friends? So don't do that, okay? So it's all about knowing this. This particular first part of algorithms is very important, my dear friend. This is where you have to concentrate more. But most of the people, they solve greedy problems. They want to solve problems, but without understanding this basic. Because in algorithms course, we are mainly interested in analyzing algorithms, estimating the complexities. That is our main aim. And learning new design techniques. That is what we learn in algorithm course, my dear friends. See, whenever you are going from A to B, both included, that is given by B minus A plus 1. Suppose 20 to 40 both included, how many numbers are there? 40 minus 20 plus 1. It is a simple mathematics, my dear friends. So here you are going from J is equal to I to N. You are going from I to N. So how many numbers are there? N minus I plus 1. That's it, issue. Nothing more. And of course we solve it like this, but most of the time what we do is we don't use this method, sir. We use big O notation. Answer will be given as big O. Here it is n times. What is the bound on J? J depends on I. J depends on I. And what is the maximum value of I? What is the maximum value of I? maximum value of I? What is the maximum value of I? N. So we take the bound of that. We take that bound. So in general, when the upper bound of loop variable depends on some other variable, we consider the largest value of the bound. Instead of using this summation, because here summation notation most of the people are afraid of it. So we use only bound for that. So here it is n times, my dear friends. So we use the bound. So it is an upper bound. It is an upper bound. It is not a tight bound. So in this particular case, we can say Tn is what, sir? N into n, big O of n square we write. And if you use this method, you cannot say theta n square as I mentioned. I mentioned theta n square very confidently because I use double summation notation. But here we use only big O notation because here it is only upper bound. It's not exact value. Tight bound, it's only upper bound. But mostly in our algorithms courses, they are going to ask you questions with where options also big O notation. So most of the people are happy with this methodology, my dear friends. They use this bound technique to find the complexities. They use this particular bound technique. Otherwise, you have to use this method, which may be beyond scope for some people. So they just use bound technique, my dear friends. Yeah, big O is safe edge notation. No trouble. No trouble at all. So you are safe. You are safe with big O notation, my dear friends. Is the idea clear? Is the idea clear? Very good. Of course, whenever you talk about time complexity, there are three types of time complexity if we talk about. Best case, the smallest running time performed by an algorithm over all inputs of size n. Over all inputs of size n, what is the best running time is what is called as best case running time, my dear friends. Worst case is the largest running time performed by an algorithm over all inputs of size n, my dear friends. See, generally average case people misread or misunderstand, sir. Average case is not, average time, it is expected time. Expected running time we call it. See, the expected values generally depends on, probability distributions. We need to write the probability distributions, my dear friends. For that, we need to find the expected values. The expected value. See, generally here it would be discrete distributions. For discrete probability distributions, the expected time is given by what's a sigma x into px, my dear friends. So we need to identify what is the random variable and what is the corresponding probability, my dear friends. Then you are going to get the expected running time, my dear friends. So that expected running time is what we call it as average time, my dear friends. Okay, average time complexity. The expected running time performed by an algorithm over all inputs of a given size. Am I clear? So that is your average case time complexity, my dear friends. See, for algorithms, we are mostly interested in worst case. Why, sir? See, worst case time complexity used to compare efficiency of two algorithms. Suppose I have two algorithms, algorithm A and algorithm B. To check which one is better, we compare their worst case time complexities, not best case, my dear friends. We compare their worst case time complexities. Why, sir? Because worst case time gives guaranteed upper bound. Because it cannot go beyond that. That is the maximum time. Am I clear? So that gives you guaranteed upper bound. So it cannot go beyond that for any input. Secondly, worst case occurs fairly often. For most of the algorithm, the worst case happens very regularly, my dear friends. And average case is, see, even though you use the probability distribution and find average case, in most of the cases, the average case time complexity would be same as worst case. So why to waste our energy and use the distribution? So generally, they use worst case to compare two algorithms, my dear friends. See, most of the time, we compare worst case, my dear friend. And whenever you talk about time complexity of any algorithm, we talk about their worst case time complexity, unless or otherwise explicitly mentioned, my dear friends. And fourth point is very interesting. Because of that, we generally talk about worst case. So who will take care of this, probability distribution and waste our energy? So they just go for worst case complexity, my dear friends. Now the first problem is linear search. Okay. See, for linear search, the idea is what happens here. What is the idea here? We are having n elements and we are searching for an element. So search, what happens, we start with first element, compare with that. That is, you are searching for an element, you compare that element with first element. If it is not equal, go for second element. Not equal, go for third element. It's a linear search, my dear friends. It's a linear search, my dear friends. हाँ, थोड़ा बहुत start कर लिए हैं. Am I clear? That's so linear search. What happens? You search the elements with every element, my dear friends. You search with every element. So best case would be what, sir? The first element is the search element. The first element is the search element. See, again, they divide this linear search into two types. One is called unsuccessful search. Unsuccessful search means the search element is not found. So when it is unsuccessful search, whether best case, worst case, yeah, average case, everything would be theta n, my dear friends. Everything would be theta n. Whereas when it is successful search, means search element is found, the best case would be theta 1. Worst case and average case would be theta n, my dear friends. See, of course, for average case, we need to talk about this probability distribution, my dear friends. That is, where is the search element found? Maybe the random variable. So, search element found in the first position, search element found in the second position, search element is found in the third position, like that we take it. Probability of finding search element at every position, we assume that equally probable. So, probability for each element would be 1 by n. Then we find expected value of this search. Then you are going to get the answer for that, my dear friends. In any way, the answer would be theta n, my dear friends. Am I clear? Of course, mostly we talk about this successful search also, but sometimes to make or to trouble you, they say that linear search result in an unsuccessful search. What is the best case time complexity? They ask you question like this. See, sorting से बहुत डर क्यों लगता है सर? Sorting के में क्वेश्चंस जो भी आया था अभी तक, इतना डरा हुआ क्वेश्चन कभी नहीं आया था. डरने की क्या बात है उसमें? Most of the people are worried about unnecessary things. See, if you are preparing for this particular examination, it is simple, sir. You are mostly worried about some unnecessary things, then it will trouble you, my dear friends. Okay? So let us see. Now next comes, before going for the next concept, that is divide and conquer recurrence relation. Yes, Nishu. Correct. That is what you written, expected running time or average case, my dear friends. Yes, correct. Perfect. See, recurrence relation we discuss in, we do recurrence relations in mathematics, discrete mathematics. Here, even in programming also we discuss, sir. Even in programming we discuss about this recurrence relations, my dear friends. Okay? Recurrence relations plays very important role. Recurrence relation means, don't read all this nonsense, sir. Simply problem in terms of subproblems. Problems in terms of subproblems. In a very vague or general sense, the meaning of recurrence means we express the big problem in terms of subproblems, my dear friends. Just express big problem in terms of smaller versions of the same problem. Smaller versions of the same problem. So recursive algorithm means what, sir? Algorithm which uses the process of recursion. So here what happens? It calls itself. So recursive algorithm or recursive function, what it will do, sir? Function is called in terms of itself. The smaller versions. That's. And some popular examples I am giving. Fibonacci sequence. See, this is Fibonacci sequence, sir. 0. Okay. 1. That is sum of previous terms is next one. 1 plus 1 is 2. 2 plus 1 is 3. 3 plus 2 is 5. 5 plus 3 is 8, plus 5 is 13, plus 8 is 21, plus 13 is 34, plus 21 is 55, and so on. And what is the recurrence relation, my dear friends? What is the recurrence relation? Just express the nth term. You take any nth term, it is sum of the previous two terms, my dear friends. Sum of previous two terms. That is, nth term is equal to n minus 1th term plus n minus 2nd term, my dear friends. But whenever you write the recurrences, you should always see that you stop it. There should be some base condition or stop condition, my friends. If you don't stop, what happens, sir? Bomb blast ho jayega. If you don't stop, what happens? It will iterate forever and ever and forever. Is the idea clear? Hope you understand. One more recurrence, very popular recurrence relation is Tower of Hanai problem. Tower of Hanai problem, number of moves to solve Tower or Hanai puzzle or Tower of Hanai problem. You all know what is this Tower of Hanai problem? You all know Tower of Hanai problem? Let me explain it. Let me write this recurrence. See, this is the problem, sir. See, actually here we have only 4 pegs or 4 discs. Okay. See, actually what happens is, the idea is you want to move these discs from start to destination. Here it is start and here it is destination using Z. So using Z, we want to move all these discs from start to destination. But here the condition is, we can move only one disc at a time. We can move only one disc at a time, and we cannot place a smaller disc below the larger disc. So with these two conditions, you have to solve this problem, my dear friends. So here, when you want to solve this problem recursively, ultimately the last one need to be replaced before last one to see. Last one should come here. If last one to be coming here, what should happen, sir? If last one should come here means, before that, the top fellows must be moved to the Z fellow, because in that particular case what happened, last one can be happy because only one disc must be moved at a time, no? So by recursive process, it is not directly, sir. By recursive process, I have to move the top n-1 disc to the middle or the temporary peg, my dear friends. So this is what happens. So here what happened, it is not directly solved. I solved a problem of size n-1. I solved a problem of size n-1. That is moved to some destination. Then what I do, this one is moved to its destination. That is one move, sir. And this is the one move. This is the one move. Now what happens, this n-1 moves by recursion. I have to move back to the destination, my dear friends. So this is your Tower of Hanai problem. So for this is Tn-1. Again you are moving it. That is Tn-1 problem. And moving this will cost you 1. So what is the cost of recursion, sir? This Tn-1 work is done 2 times. That is 2 Tn-1. And moving one disk, that is plus 1, my dear friends. So this would be the cost of recursion, my dear friends. See, my dear friends, I am not at all solving any problem, not at all discussing complete problem. Overall overview I am trying to give. The basic idea of this algorithm formula is overview, and I am interested in the basic concepts than any particular for sorting algorithms. I'll give you all sorting algorithms, their complexities and their properties I'll discuss, but not in detail, because if I need to discuss every problem, will take that much time, sir. See, within some time we need to cover all the formulae, my dear friends. Okay, so why I am doing more work on the initial formula, because initially there are so many mathematical things where most of the people worried, and because of that lack or problem with mathematics, they are unable to do the algorithm stuff simple. The algorithm work is very simple, sir. Solving the problems is very simple. Once you solve a problem, this kind of recurrences we have to create. This work is very important. Next, solving recurrences, that is the secondary part that can be done very easily. Of course, this problem can be solved using iterative method, or I'll give you a simple method. With that method also you can solve this problem within no time, my dear friends. Just remind me, I solve this problem with a simple formula which I am going to give you in a while. I'll give you a formula, in a while I'll solve this problem within no time, my dear friends. There are many methods to solve recurrence relation, that is iterative method. This is iterative method means what, sir? Once you have some problem like Tn is equal to say Tn minus 1 plus n, then Tn minus 1 is expressed, that is what, Tn minus 2 plus n minus 1. So you are going to substitute the values. So this iterative process we call it. Here iterative process, there are 2 methods which people follow, either forward iteration or backward iteration. That is, starting from stop condition they move to that bigger value, or from bigger value, this is called backward iteration, my dear friends. There is one more thing called forward iteration, where T1 we build T2, from that we build T3, then we write T4, then we write the general expression, my dear friends. So So that is iterative method, my dear friends. The next one is linear recurrence relation. Generally this we discuss under discrete mathematics. I just give you idea of this, my dear friends. Substitution method. See, generally people call this as substitution method. This substitution is a verification method, sir. This is a verification method. See, verification means after guessing a solution, we have to verify whether it is correct or not. That is substitution method. Of course, we are not discussing now. Recursion tree method means we are going to create a recursion tree. Generally for recursion algorithm, this recursion tree method, generally for divide and conquer type of recurrence relation, this recursion tree method will work. Otherwise, we have one thing which is known as the master theorem, which helps you in solving many problems, my dear friends. So now what we do is we'll see master theorem and its variants, and subtract and conquer variant also we'll try to see. The linear recurrence relation, my dear friends. This is the general form of linear recurrence relation. C naught an plus c1 an minus 1 plus and so on ck an minus k is equal to fn. See, here you see all these fellows are having power 1. They are not multiplied with each other. Such fellows are called linear recurrence relation. You are going up to n minus k, so they call it as of degree or order k. Some people also call it as order k. Some people call it as degree k, my dear friends. And if fn is 0, you call it as homogeneous. Fn is non-zero, we call it as non-homogeneous. I am interested in only in this homogeneous fellow, sir. I consider a second order homogeneous linear recurrence relation. Whenever they give you this problem, for example, I am having a problem like an plus 5an minus 1 plus 6an minus 2 is equal to 0. What I do is I create what is known as characteristic equation. Creating this is very simple, sir. This fellow's order is 2, no? So you create t square, then t, then constant. T square coefficient is, what is coefficient of this one? T coefficient is, what is coefficient of this? Plus 5. Next constant is what? 6 is equal to 0. Similarly here also you see t square, t constant. Coefficient of this is 1, that is used here. K1 is used here, K2 is used here. You equate it to 0 and find the roots. Based on the roots we are having solution, my dear friend. Based on the roots we are having solution. Yes. See, the substitution and iteration people confuse, sir. See, some people call the iteration method itself as substitution method. I am calling them as separately, my friend. Nothing more than that. So sometimes roots may be real and distinct. In this case, roots are like, minus 2, minus 3. In such case, this is the general solution. C1 into B1 power n plus C2 into B2 power n. So for this problem, the solution is C1 into minus 2 power n plus C2 into minus 3 power n, my dear friends. So we directly know the form. Suppose if the roots are real and equal, for example, if you are having problem like, an minus 4a n minus 1 plus 4a n minus 2 is equal to 0, then the roots characteristic equation is t square minus 4t plus 4 is equal to 0. The roots would be 2 and 2, my dear friends. In this particular case, the general solution is given by c1 plus c2n into b power n. That is c1 plus c2n into 2 power n will be the solution, my dear friends. Of course, the same idea can be extended, generalized for third order differential equation or third order recurrence relation also, my dear friends. Now, the first design strategy, that is divide and conquer recurrence relation. And mostly the divide and conquer recurrence relation which are solved in your algorithm course can be solved mostly using master method. Am I clear? So first let us understand what is this divide and conquer method. See, in divide and conquer method we are having a problem of size n. The problem is divided into sub-problems of size maybe n by 2, n by 2, sir. See, here I divide into 2 sub-problems. It's not necessary that you divide into only 2 sub-problems, sir. Sometimes you may be dividing into 3 sub-problems, 4 sub-problems or B sub-problems. And there may be problems where you divide the sub-problems of different sizes also. That is also divide and conquer only, sir. But we are considering a very, very simple situation where you divide the problem into 2 sub-problems of equal size, my dear friends. Am I clear? Okay. See, in divide and conquer problems, when you divide the problem into sub-problems, sometimes not all sub-problems need to be solved. For example, if you take binary search, okay, when you take binary search, only one of the sub-problem is solved. But if you take merge sort, both the sub-problems need to be solved. It depends on the problem type, my dear friends. Even though you may divide into sub-problems, many sub-problems, B sub-problems, only A of them need to be solved, my dear friends. Am I clear? So first you divide them, and You just express problem in terms of sub-problems. The sub-problems are expressed in terms of their sub-problems. They are expressed in terms of their sub-problems, like that. So these sub-problems are solved recursively. These sub-problems are solved recursively, my dear friends. So you conquer them, the sub-problems. So ultimately what happens when you solve them recursively, what happens? The original problem is divided into sub-problem, they are divided into sub-problem, they are divided into sub-problems, like that it happened. Now you solve them. Conquering means solving the sub-problems. When you solve the sub-problems, what happens? You move to this first level sub-problems, my dear friends. So you got a solution to sub-problem 1 by recursive process, you got solution to sub-problem 2 by recursive process. Now you combine them, my dear friends. And then you are going to get solution to the original problem. In some problem, this step may be missing. Combination is not required, sir. Directly when you conquer the sub-problems, automatically you are going to get the solution for the full problem, my dear friends. Only the cost of dividing may be mattering there, my dear friends. But some problems require this combined step also. For example, quicksort may not require this combined step. Okay, quicksort may not require this combined step, my dear friend. There the partition plays very important role. Whereas in merge sort, this divide step is constant time, but the combined step takes order n time, my dear friends. So it depends on the problem type, my dear friends. In some problems this will play very important role. In some problems this divide step play very important role or take extra time, my dear friends. And most of the divide and conquer recurrence relation result in this particular form of recurrence relation, which is called divide and conquer recurrence relation, which is of the form Tn is equal to A into Tn by B plus some Fn, where A is greater than or equal to 1, B is greater than 1. A can be 1 or more, B should be strictly greater than 1. It cannot be 1, sir. It can be greater than 1, my dear friends. So based on the different cases, we have solutions for this divide and conquer recurrence relation, my dear friends. See, generally we compare n power log A to the base B with Fn, my dear friends. Generally we compare these two. So the different cases based on this, my dear friends. The first case is Fn is big O of n power log A to the base B minus epsilon. See here, n power log A to the base B, even from A if you subtract something also, still it is dominating Fn. That is, which one is larger? When case 1, this is larger. Case 1, n power log A to the base B is larger. Even when you subtract something, still it is dominating. So in that particular case, the complexity is simply big theta of n power log A to the base B. N power log A to the base B is the complexity, my dear friends. The second situation where both are having equal order of growth. Both are having equal order of growth. They are of equal order of growth, my dear friends. Same order of growth. Then the complexity is simply theta into, either you can say n power log A to the base B into log n, or Fn into log n, my dear friends. Either you can write it or you can write theta Fn, because Fn and n power log A to the base B both are having equal order of growth, my dear friends. Fn into log n, my dear friends. And the case 3. The case 3 is, this fellow is dominating. Here Fn is dominating. Fn is dominating, but when Fn is dominating, we can't directly write the answer, sir. Case 3, Fn is dominating, but in this case, we also need to see one condition called regularity condition. If the regularity condition also satisfies, then we take Fn is, or the time complexity is theta of Fn, my dear friends. Mostly, if Fn is polynomial, regularity condition is 100% satisfied, sir. For other type of functions, you have to verify, my dear friends. And this is the regularity condition, my dear friends. A times f of n by b is less than or equal to c times fn, where c is a constant less than 1, my dear friends, for large n values. You have to verify this condition also, my dear friends. Some people directly take everything granted, because mostly we get fn's as polynomial fellows, so generally it works, but for other functions you have to verify, my dear friends. There is a variant of divide and conquer which is very useful for quicksort algorithm. If Tn is of the form T of alpha n plus T of 1 minus alpha n plus beta n, this is fixed, beta n. In this particular case, if the value of alpha lies between 0 to 1, see, it's like, Tn is equal to T, not P, Tn by 4 plus T 3 by 4n plus some phi n. So it is alpha is what, sir? 1 by 4, and it is 1 minus alpha. Whenever it happens, whenever you get such recurrence relation, simply time complexity is theta n log n, sir. Without doing anything, you can say theta n log n is the answer, my dear friends. Simply theta n log n is the answer. And there is one more variant. See, sometimes it may not, because if you don't use this method, you have to go for recursion tree method, sir. If you don't understand this method, you have to use recursion tree method, and that also gives you an approximation that need to be verified using substitution method. Who will do all that stuff? Because generally in GATE examination, whatever problems they ask, they will be based on some standard results only. Okay, so we just need to understand it comes under which format. That is our work. Mostly the problems which are asked, which they are going to ask in GATE, will be based on standard formats, my dear friends. If you can identify them, it would be sufficient. So here you see, like t n by 2, t n by 3 plus some 5n. So you see 1 by 2 plus 1 by 3. You just check whether it is less than 1 or equal to n. So here LCM is 6. So you get 3 plus 2, which is 5 by 6 less than 1. So based on this, if sum of sizes of subproblems is less than size of the problem, the complexity of this is theta n. So the complexity of this would be theta n, my dear friends. If the sum of sizes of subproblems is same, for example, if I say Tn is equal to, say Tn by 2 plus 2 times Tn by 4 plus 5n or 6n, whatever it is. Here what happens, it is 1 by 2 plus 1 by 4 2 times. Sum of size of subproblems is equal to 1. In this particular case, the answer would be theta n log n, my dear friends. So you can use it. Of course, it is based on the recursion tree idea only. It's a small variant which we can use for solving problems, my dear friends. And there is one more thing called, some people call it as muster theorem. It's a subtract and conquer theorem, my dear friends. Here, Tn is of this particular form, C, when C means constant for n less than or equal to 1. For n greater than 1, it is A into Tn minus B plus some Fn, where Fn is of the form order n power k. Of course, this first case generally never happens, but for completeness we are writing it. When A is less than 1, that is A value say 0.5, 0.2, 0.3, something like that, then Tn is simply order n power k, my dear friends. Whatever Fn is there, same order will be for Tn, my dear friends. But when A is 1, in that particular case, Tn will be order n power k plus 1. For example, if you are having Tn is equal to Tn minus 4 plus n cube. So here A is 1, then Tn, suppose here what is Fn, sir? Fn is of order n cube, na? Then Tn will be of order n power 3 plus 1. It is of order n power 4, my dear friends. But the case when A is greater than 1. See, this is what happened for our, Tower of Hanai problem. Tn was what? 2 times Tn minus 1 plus 1. That is Fn is of order 1 or n power 0. So in this particular case, Tn will be what, sir? Tn will be of order n power k. N power k means n power 0 into A. What is A? 2 power n. N is n only. B is what, sir? B is 1. So it is big O of 2 power n, my dear friends. So of course you can use that iterative method to verify this, or by this simple subtract and conquer variation also you can find the time complexity, my dear friends. For most of the problems, one of these categories we can easily find the time complexities, my dear friends. Okay, there will be some other problems. You can identify how many variant problems they asked. You can easily identify. They can be solved either using recursion tree method or iterative. Mostly iterative method will work, my dear friends. Of course, you see, if you see in the market, people are worried about solving every damn problem in the world. They are worried about creating more mess. Okay, they want to mess up with this problem. That you can do it, my dear friend, leisurely. Okay, for GATE point of view, you can verify previous questions. You don't have to believe my words, sir. Just go back and take BYQs, what questions they ask, you see. Am I clear? That is enough. See, if you go on creating problems on your own and want to solve every type of problem, there will be many problems, sir. Am I clear? Of course, not every problem can be handled with our basic results only. But in GATE, generally, they will be worried about only the problems which can be generally handled with basic results or which can be reduced to basic result. For example, you get this, root n problems like nonlinear recurrence relations. They all can be solved by reducing it to some of these forms, my dear friends, very easily. Am I clear? The binary search problem, it is a searching method which is applicable only when the list is a sorted list, my dear friends. So here what happens, we first compare the search element with mid element of the array. Am I clear? If x is equal to mid, then desired element is present in the list. If x is less than list, then we find the element, or we search the element in the left list. Otherwise, if x is greater than a mid, we search the element in the right list, my dear friends. Now in this particular problem, what is the time complexity, my dear friends? What is the time complexity? See, either you search in the left sublist or you search in the right sublist, my dear friends, plus the amount of time taken for finding mid element and comparing that mid element with search element. So that is some constant time, my dear friends. Of course, people write +1, or you can write plus constant, my dear friends. You can write, because you are not solving both the subproblems, either left or right subproblem only you are solving. It is not 2 times Tn by 2, it is only Tn by 2 plus constant. +1 you can write it, or plus some constant you can write it, my dear friends. Am I clear? This is for n greater than 1, my dear friends. Suppose if n is equal to 1, it is some constant time, my dear friends. Is the idea clear? So this was a direct gate question. You can expect such questions. They ask you what is the recurrence relation for the problem. This is a very famous question, my dear friends. Please note that. All of you able to follow? So what is the answer for this? Please answer the question, my dear friends. Yes, Nitya, you are doing very well. Super. Cool. And there's a test series offered by BYJU'S, my dear friends. The test series is at our affordable prices for all the branches, my dear friends. You can purchase this test series. It is the test series is curated or created by the expert people, okay, who are having very good expertise in this. Okay, so you can attend these test series, my dear friends. So what is the answer for this? A is the answer. Direct question, my dear friends. Now there is a password for this PDF file, my dear friends. The password is, what is the password? Okay, let us use all small letters. Algo 323. So please note, this is the password for the PDF, my dear friends. Don't share it with anyone. Happy Diwali, sir. I know that people, Sridhar, you want? No, I already given Sri, no? So that is your password for this PDF, my dear friends. So the merge sort. See, merge sort is you are having a array of n elements. You want to sort it. In merge sort algorithm, 23 है last में. Yes, algo 323. Yes, it is there. Suppose, see here generally we have P means the leftmost element index, and R means the rightmost element index, my dear friend. If the leftmost index and leftmost index is smaller than rightmost index, then you continue the process. You repeat the process, my dear friends. So here we are going to find mid element, which is P plus R by 2. Floor we find it, okay, that is floor. See, finding this will take theta 1 time, sir. Then what happens? You call this merge sort for the left subarray. That is, you recursively solve left subarray using merge sort algorithm. Then recursively solve the right subarray using merge sort algorithm. That is, P to Q, Q plus 1 to R, you are going to apply this merge sort. See, this will take Tn by 2 time. This will also take Tn by 2 time, because entire problem will take Tn time means this left sub problem will take Tn by 2 time, right sub problem will take Tn by 2 time, my dear friends. So that would be 2 times Tn by 2. So combining these two, Tn by 2 plus Tn by 2 is 2 times Tn by 2. This is combined solution, my dear friends, sum of these two. Then comes, means after recursively solving, you get left sorted subarray and right, this is also sorted subarray. We need to merge them in a sorted manner. And that is called merge process, my dear friends. This merge process will take theta n time, my dear friends. This merge process will take theta n time, and the complexity for merge sort would be what, sir? Merge sort complexity would be what? Of course, it is not given. Time complexity might be given in the next one. Actually, we call this problem for one first index and last index, my dear friends. Of course, if you are writing C programming, it may be 0 to n minus 1. But in algorithms, generally our indices start from 1, my dear friends. So 1n it would become. So the recurrence relation for this would be like, 2 times Tn by 2 plus theta n. See, maybe there may be some additional constant, but they are all, hardly matter, so that all can be ignored when you write theta n, my dear friends. And this is theta 1 when it is a size of the array is 1, my dear friends. So whatever case you take, this is the recurrence relation. Whether you take best case, worst case or average case, in all the cases, this is the recurrence relation, my dear friends. So the time complexity in all the cases is theta n log n, my dear friends. So whatever case is there, this is the recurrence relation. And by Master theorem, you can apply Master theorem, my dear friends. By Master theorem, the time complexity of this recurrence relation is Tn log n, my dear friends. Yeah, same time complexity for all the cases, my dear friends. Yes. Quicksort algorithm. See, in quicksort, of course, we have low index. In the previous problem, I said P and R. Here I am saying low and highs are nothing more than it. As long as low is less than high, you continue this. What you do here is, here we try to take an element, and what you do is you call partition. That is, we try to select one element, my dear friends, and we try to find the correct position of that particular element. That is what we call it as. Yes, sir, Nishu Kumar, I think I already told you. Yes, partition is called A, low and high. So what happens when you call this partition? What happens? One particular element is taken. Generally, the first element is taken as pivot element, and we try to find the exact position of that. Okay, in such way that all the elements smaller than that would be placed left, and all the elements larger than that would be placed right. That is, we place an element at exactly the correct position. Okay, one element is placed at correct position, my dear friends, and it will take theta n time, my dear friends. Now you call this quicksort on the left subarray, and you call quicksort on the right subarray, my dear friends. But here the problem is, this may take theta n time. What is the size of, where is this j actually matters, my dear friends. So in the best case, that j divides the array exactly into two parts. J exactly divides the array into two parts. So you get left subarray size is Tn by 2, right subarray size is Tn by 2, my dear friends. Am I clear? So this occurs when the subarrays are equally, completely balanced every time. And what happens? 2 Tn by, that is Tn by 2 left subarray, Tn by 2 right subarray. So 2 times Tn by 2 plus partitioning takes theta n time, my dear friends. So this would be the recurrence relation, and we know the time complexity for this is theta n log n, my dear friends. Now what is very interesting is the average case. See, on an average, where it can be divided, my dear friends. So it may be divided at some portion. See, that portion can be anything, my dear friend. It can be equally designed, my dear friend. So that may be 1 by 10, 1 by 2, by anything. 1 by 10, 1 by 9, 1 by 7, 1 by 8. Anywhere it can cut, my dear friends. So this would be the recurrence relation for your quicksort on average case, my dear friends. Partition can happen any side, my dear friend. On an average, it can cut anytime, because you may get some balanced splits, you may get unbalanced splits. So we generally call it as unbalanced split. See, completely unbalanced split, I'll tell you, this is partially unbalanced. It's not exactly balanced split, but you may get a split like a general split may happen like alpha n one side, 1 minus alpha n one side. But if you remember, I given time complexity for this, my dear friends. What is the time complexity for this? Theta n log n to the base 1 by 1 minus alpha, which is nothing but base of logarithm does not matter, theta n log n, my dear friends. So on an average also, the quicksort time complexity would be theta n log n, my dear friends. But whereas in worst case, what happens? See, it so happened that the partition element or the pivot element is the first element itself. So what happens? You get a completely unbalanced split. One side Tn minus 1 and one side is 0 problem. So it is Tn minus 1 plus n, and when you find the time complexity, it would be theta n square. See, even though the worst case time complexity of quicksort is n square, mostly quicksort performs average case, or quicksort gives average time complexity, my dear friends, more often. Am I clear? So this partition exchange sort also people call it, quicksort also we can call it. And even though worst case complexity is theta n square, mostly quicksort performs this in worst average case, my dear friends. Unlike most of the algorithms perform their worst case time complexity more often, but quicksort more often performs its average case complexity, my dear friends. Most often performs its average time complexity. And quicksort works, get this worst case time complexity when the array is already sorted. When the array is already sorted, this fellow works bad. So quicksort is a bad algorithm for already sorted algorithms or already sorted arrays, my dear friends. We'll try to see all that, my dear friends. We'll try to see. Okay. Everything Nishu Kumar, I'll give you the list total. Okay. So best case, worst case and average case. Am I clear? See, of course, it is solving within that. Now you are not, are you using, see, in place, suppose some people don't know what is that in place. See, in place means extra space used by quicksort algorithm. Extra space used by quicksort algorithm is constant only, so it has to be in place algorithm only. Am I clear? It has to be in place algorithm. Now best case is theta n, worst case is theta n square, but average case is theta n log n. But quicksort performs this average case complexity more often, my dear friends. Quicksort gives you average case time complexity more often, my dear friends. There is something called kth smallest element. For that also you can use this particular quicksort idea only. So we use partition algorithm of quicksort, find the kth smallest element. So you use that jth smallest element. So you got jth smallest element. Okay, then what you do? Suppose you want kth smallest now. If k is j, you done. Your work is done. Suppose if k is less than j, you have to perform the quicksort on only left subarray. Because that kth smallest element will be only on the left subarray. So you have to do it on only left subarray. Find kth smallest in 1 to j minus 1. Suppose if k is greater than j, you have to find k minus j, because already here how many elements are there? J elements are gone. You want to find kth element means what? K minus jth element you have to find in the right subarray, my dear friends. You have to find k minus jth element, my dear friends. No extra element. Very good, Nitya. So as I told you, if k is equal to j, that is the best case, sir. But average case is very interesting. See, average case may happen. See, average case means you may find that pivot element anywhere, no? So depending on that, either you are taking either left subarray or right subarray. So one of them will be like Tn by 2, or it may be Tn by 5, or it may be T4n by 5, whatever it is. These are the different possibilities, my dear friends. These are the different possibilities. And by master theorem, you can find that complexity for all these will be theta n only, my dear friends. For all these, the time complexity will be order n only. But the worst case happens when you have that jth element is on one side and remaining n minus 1 work you have to do it. That is Tn minus 1 plus n. In this case, the time complexity will be theta n square, my dear friends. So in any case, best case or average case, the complexity would be theta n, my dear friends. It's theta n only, na? N power log a to the base b. Theta log n. Am I clear? It would take theta, because n plus this will take n and this will take log n. N plus log n would be what, sir? Theta n complexity. Theta n complexity. So kth smallest element complexity, worst case would be theta n square. Best case or average case would be theta n, my dear friends. There is one problem called Strassen's matrix multiplication. See, the idea of Strassen matrix multiplication is, if you are having n by n matrix, it's actually multiplied using this block matrices, my dear friends. So you divide into n by 2 by n by 2 matrices. Am I clear? So you want to multiply two matrices, then you divide into n by 2 by n by 2 matrices, my dear friends. So these are the matrices, my dear friends. Like this is sub matrices. So you can multiply two matrices just by multiplying corresponding blocks also, my dear friends. But if you use regular procedure, A into E plus B into G will give you I. A into F plus B into H will give you J. See, if you consider like that, 1, 2, 2 multiplications for one element. So for 4 elements, 4 into 2, 8 multiplications has to be done. And each fellow is of order Tn by 2. See, if your original problem is of size Tn, you are doing this n by 2 problems, how many? 8 sub problems you are doing. So 8 into Tn by 2, my dear friends, plus what happens? See, plus what happens dividing into n sub problems. You have to add them, na? Those fellows. That cost would be theta n, my dear friend. Because after multiplying, you have to add those fellows, na? That would be of order n, my dear friends. But it's not dynamic programming, it is divide and conquer, sir. But you can get this instead of 8 multiplications by using this special matrix multiplications. You can get this IJKL just using 7 matrices. See, only 7 matrices, and here you see 1, 2, 3, 4, 5, 6, 7 multiplications you are doing. So instead of 8 multiplications, you can do it with 7 multiplications, my dear friends. So what happens? Okay, of course, this is theta n square, sir, because you have to, that extra work would be theta n square. Sorry for that. See, normally it would be Tn is equal to what? Tn would be what, sir? Because you have to, n by 2 by n by 2 means what, sir? How many elements are there? N square by 4 means n square elements need to be added, na? N square elements need to be added. So that is 8Tn by 2 plus n square. Here also let me write that. Normally it is 8Tn by 2 plus n square, my dear friends, if you don't use this Strasson's matrix multiplication. But if you use it, you can do it with 7 multiplications only. See, the advantage is if you use it, it takes order n cube complexity. But if you use this method, it will take order n power log 7 to the base 2 complexity. Log 7 to the base 2 is nothing but n power 2.81. You got better complexity or not? You got better complexity or not? That is the advantage of Strasson's matrix multiplication, my dear friends. Is the idea clear? See, the idea here, what we need to understand is, of course, time complexity you can remember, and the recurrence relation is what is very, very important. That is what this Strasson done is, instead of doing this 8 multiplications, he created new matrices. With 7 multiplications only, he could able to create this IJKL. So he could able to reduce the complexity from n power 3 to n power 2.81, my dear friends. He got better complexity, my dear friends. Of course, dynamic programming, it's a design technique based on the principle of optimality. What is this principle of optimality says, sir? See, no one is going to ask you those matrices, sir. If you are writing your university examination, they'll ask you. In university examination, somehow you remember and write down, sir. They don't take exact matrices, my friend. Somehow you can remember the order. Some here and there you write it, you can do it, no problem. But GATE, they're not going to ask you all the matrices, my dear friends. Such type of questions will not be asked in GATE examination. Not for 2 by 2, sir, anything. No. Divide and conquer, it works for anything, sir. Even if n is not even, they'll introduce some additional 0 rows or columns and they use that particular method. It is working for any matrices, sir. Any matrix of order n, my dear friends. See, these ideas are not for small values of n, sir. See, all these design strategies we are discussing are for asymptotic, large values of n, not for small values of n, sir. Please remember. Okay. It's a dynamic programming is a design technique based on the principle of optimality and an optimal sequence of decisions. What is this principle of optimality, sir? An optimal sequence of decision has the property that whatever initial state and decision are, the remaining decisions must constitute, whatever initial state and decision you take it, the remaining states must constitute an optimal sequence of decisions with regard to the state resulting from the first decision, my dear friends. See, if the sequence of decisions must give you the optimal result with regard to the state resulting from the first decision means the problem must be expressible in terms of sub-problems only. Then only it is happening. See, the sequence of decision, whatever first decision is made, based on that whatever state happened, from that the remaining sequence of decisions must give you optimal solution means the original problem must be in terms of sub-problems. Then only it happens. So that actually it says what, sir? We should have problem can be expressed in terms of sub-problems. Okay? Then what happens? That is what we call it as optimal substructure. That is what we call it, this principle of optimality, also called as optimal substructure, my dear friends. Okay, of course, bottom up computation, my dear friends. We start from lower order values, then we are going to compute the big values. See here what happens, we can see solution of the problem as result of sequence of decisions. Okay, now what is very important is the elements of dynamic programming. The first one is optimal substructure. This is what you call it as recurrence relation, my dear friends. So you can express problem in terms of sub-problems. But here what is very important with dynamic programming is the same sub-problem is solved many times. Same sub-problem is solved many times. That is what we call it as overlapping sub-problems. So when the problem is solved many times, you are wasting a lot of energy, time. So what they do is they store it and reuse it, and that is what you call it as memoization. The memoization process means store and reuse it. Don't recompute it. Store and reuse it. That is what you mean by memoization, my dear friends. So these are the three characteristic or elements of dynamic programming, sir. First, we have to express problem in terms of sub-problems. Then we need to identify overlapping sub-problems. So when the problems are solved again and again, instead of solving it again and again, store it and reuse it. That is the idea of dynamic programming. See, dynamic programming is nothing to do with your programming, sir. It is a tabular method. In good olden days, what they used to call this tabular methods as programming, my dear friends. So it is a tabular method where we store the values and we reuse them. Because overlapping sub-problem means same sub-problem is solved many times. So when you identify that same sub-problem is solved many times, we solve it and we store it somewhere. So whenever you find same sub-problem, instead of solving it, we reuse that, my dear friends. And that is the idea of dynamic programming. And my dear friends, I see this, the problems based on dynamic programming, people solve it by direct methods. Then what is the use of dynamic programming, sir? Okay, so one should always know how to use dynamic programming, my dear friends. Okay, so let us start with this matrix chain multiplication. What is important for this dynamic programming, sir? Of course, problem solving method I cannot explain in this formula series. I'll just give you the idea for this dynamic programming, that is recurrence relation. Then the complexity I'll discuss, my dear friends. Okay, so these are the two things which are very, very popular, very important for GATE point of view. So I'll quickly give you the recurrence relation which we need to remember. So similarly, when you make your short notes also for dynamic programming or for greedy algorithm, of course we have optimal substructure, but we generally don't use it because in dynamic programming there may be many sub problems or many decisions are there. We consider everything, whereas in greedy method, even though we have optimal substructure, we only consider the one which looks optimal at that particular moment. Okay, what is best at that particular moment, we consider that and we move on to that particular phase, my dear friends. That is not the case, my dear friends. In dynamic programming, we try to see with all these sub problems what is the resultant best solution you are going to get. Okay, so dynamic programming will guarantee the solution, whereas greedy does not guarantee the solution, because at that moment we see problem in terms of sub problem. What looks best, we just move on to that particular route, my dear friends. Okay, of course there are some problems for which greedy works and it works wonders. In greedy, the verification of correctness is difficult, but methodology is simple, whereas dynamic programming, the verification of correctness is very easy, but the application of the method is difficult, my dear friends. Yes. So in the matrix chain problem, what happens? We are having n matrices. What is the best order to multiply, my dear friend, without changing the original order of the matrices? That is, if you are having 3 matrices, M1, M2, M3, whether I should multiply M1, M2 and the result to be multiplied with M3, or whether I should multiply M2, M3 first and the result to be multiplied with M1. Because matrix multiplication is associative, the order in which you multiply does not matter, because matrix multiplication is associative. Any order is fine, my dear friends. Okay, but some orders are cheaper than other orders. So which order is better, we need to identify. And for that, we are going to use what is known as dynamic programming approach. Let me give you the idea for this. Here we assume that first matrix is of order R0 by R1, second matrix is of order R1 by R2, like that last matrix is of order Rn minus 1 by Rn, my dear friends. Of course, we already told you about this. Some orders are cheaper, we have to find the cheapest order. Okay, so the idea for dynamic programming goes like this. See, when you want to multiply this m1 to mn, so we assume that somewhere we have to cut, na? Somewhere we have to cut. Suppose k is the place which gives you, when you divide at kth matrix, you get best order. So cost of this would be like, suppose the cost from m1, okay, here what he says is, instead of writing m1 to n, intermediate problem is solving. Intermediate problem can be generalized to full problems. Mi to mj may be cut. So the cost from mi to mj is say mij, then cost from mi to mk is what, sir? It would be mik. Then cost for solving this problem is mk plus 1j, my dear friends. But after getting these two problems, we have to multiply them to get the full solution. So the cost for multiplying these two matrices would be, the resultant matrices would be this, my dear friends. So generally people don't think about it, that is very important. And this gives you the recurrence relation for matrix chain multiplication, my dear friends. And if you see the time complexity, let me clear this. See, the advantage of dynamic programming, you will try to understand here, sir. We will try to understand the advantage here. Suppose if you use the brute force method, because the number of multiplication orderings possible for n plus 1 matrices is given by Catalan number. This is called Catalan number, sir. When you are having n plus 1 matrices, the number of multiplication orderings is given by Catalan number, which is 1 by n plus 1 into 2 NCL. So this many orders you have to consider. For every order you have to find how many multiplications are required. And for that it is given by this Catalan number is having this 4 power n by n power 3 by 2 as the lower bound, my dear friends. Okay, that is the complexity if you use direct method. But whereas if you use dynamic programming method, we can do by order n cube, my dear friends. Order n cube, we can complete the entire solution. We can solve this problem in theta n cube, because just we are going to use this matrix, my dear friends. This formula will give you the answer. We are just going to use this n by n, and we need to fill the elements, my dear friends, and it can be done in theta n cube complexity, my dear friends. Am I clear? The next one is longest common subsequence problem. See, given two sequences x and y, a z is common subsequence of x and y if z is a subsequence for both x and y, my dear friends. So some examples you can take: x is this, y is this, and some common subsequences are, say, BCA. See, BCA. Here also we have BCA, and we have some BCBA, 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 BC, sorry, not this, BCBA, like that. See, subsequence means what, sir? It is obtained by deleting some symbols from anywhere, sir. So we have to identify common subsequence, my dear friends. So these are some common subsequences. Out of that, we have to find the longest common subsequence. So what is the longest common subsequence? Both BCBA and BDAB are the longest common subsequences. So for finding this longest common subsequences, okay, so we define this Kij, which is length of longest common subsequence from x1 to I and y1 to j, my dear friends. And this is a formula, sir. See, this idea goes like this, sir. 1 to I, y, 1 to j, my dear friends. See, when you have this sequence 1 to I and 1 to j, consider the last symbols. See, last symbols, that is at ith index and at jth index, the symbols may be matching. That is xi is equal to yj. See, if xi is equal to yj means what, sir? You already got one length. So you already got one length, one common symbol is there. So we just need to do remaining subproblem. What is remaining subproblem? 1 to I minus 1, 1 to j minus 1. In this subproblem, we have to identify longest common subsequence. So the problem would be ci minus 1, j minus 1 plus 1, my dear friends. Suppose I'll write 2 times the same thing. I'll explain why. Suppose if ith symbol and jth symbol of x and jth symbol of y are not matching. So if they are not matching means what we need to see, sir? What we need to see? Because these are not matching, either you have to consider this subproblem or you have to consider this subproblem. Whatever gives you maximum, that you have to consider. This is nothing but what? xi to j minus 1 or xi minus 1 to j. Whatever is maximum, that you have to consider when xi and yj are not matching. That is the recurrence relation, my dear friend, nothing more. Direct recurrence relation. That is the recurrence relation for longest common subsequence. Hope you understand. Of course, I need to clear this to show you the time complexities. See, if you don't use the divide and conquer recurrence relation, the time complexity brute force would be, you have to take every subsequence of second one that has to compare with every sequence here, my dear friends. So it would be of order n into 2 power m or m into 2 power n, my dear friends. And if you use this, dynamic programming approach, the complexity would be simply order n into m, my dear friends. You can solve it using order nm complexity, my dear friends. So that is the beauty of this divide and conquer approach. Of course, similarly, we have this Warshall algorithms, which finds all pairs path. It's not a path, all pairs path algorithm we call it. Of course, the recurrence relation. See, the basic idea is from I to j, whether there exists a path or not. Okay, what it will do is, see, we use symbols or how many we label the vertices. So number of or the paths using k symbols. Okay, that is vkth vertex is used or vkth vertex is not used to reach from ith vertex to jth vertex when you are considering. So those two, because in recurrence always what happens, what are the different possibilities from ith to jth vertex without using kth vertex or with using kth vertex if you are reaching. So whatever is the best one, because whatever gives you the path, that you consider. If both gives the path, anyone you can consider. So here we are only interested in the path, my dear friends. So in this particular case, Rijk, that is I to j using k as intermediate vertex. K as intermediate vertex. So see, without using, if you are getting path, that you consider, or with using the intermediate vertex as k, you are getting the answer, you consider that, my dear friends. So this would be the recurrence relation for that, my dear friends. And of course, for getting this recurrence relation, you can use simply, matrix multiplication type of algorithm. Order n cube would be the complexity. Order n cube will be the complexity. Suppose if you don't use this dynamic programming algorithm, the complexity would be order n square into 2 power m, my dear friends. Because order n square means for every pair of vertices, you have to consider all possible paths, my dear friends. But if you use dynamic programming, you can do it in theta n cube, my dear friends. See, all pairs shortest path algorithm and all pairs path algorithm, that is Warshall algorithm, both are same. Here we just consider whether the path is there or not, whereas in all pairs shortest path algorithm, we also consider the cost. And out of these two, whatever is the shortest, that you are going to consider. So instead of this, here OR operation you use, there what happens, you find this cost and you find this cost. Whatever is the minimum, that you are going to consider, my dear friends. That is Floyd-Warshall algorithm. The idea would be the same, my dear friends. So this would be the recurrence relation for this. Dij whole power k minus 1 means without using kth vertex as intermediate vertex or with using kth vertex as intermediate vertex, whichever is going to give you the minimum cost, that you are going to consider, my dear friend, because you want shortest path. And of course, this also can be solved if you don't use the dynamic programming, the cost would be order n square into 2 power n. But if you use the dynamic programming approach, it is theta n cube will be the cost, my dear friends. Okay. Of course, there is one more thing called 0-1 knapsack problem. The 0-1 knapsack problem is, see here we are having, n objects. Each is having some cost, weight as well as cost associated with it. And we are having a knapsack or a bag or a box, whatever it is, of capacity C, and you have to select the items. Like you are a thief, you want to select items in such a way that you go away with the maximum profit. That is your 0-1 knapsack problem, sir. Even this can be solved using your dynamic programming approach. Of course, the Vij is value of the most valued subset of first I items fit into the knapsack of capacity J. First I items, out of first I items, what is the best I items or best items which can fit into knapsack of capacity J, my dear friends. So in this, what happens? See, there is a ith item. Ith item is there, no? So suppose the weight of the ith item is smaller than knapsack capacity, that is J minus Wi is greater than or equal to 0. Means there is a possibility that this ith item can be put in your knapsack. In that particular case, without putting that what is the cost, with putting that what is the cost, you have to consider. Out of these two, whatever is best, that you have to consider. That is, ith item can be part, but if it is part of that, whether it gives you the best price or not, you have to check it. Suppose if you use it, profit of ith item and remaining I minus 1, what is the profit you are going to get? This is without using ith item, what is the profit? Out of these two, whatever is the best, that you are going to consider. And the other possibility is Wi, ith item cost is more than the capacity of knapsack, you cannot use that. In that particular case, you just consider this Vi minus 1 J, my dear friends. So this would be the recurrence relation. See, in dynamic programming, the basic idea is how to write this recurrence relation, my dear friends. This plays very, very important. We should know, because they can ask you the recurrence relation directly, and the second thing which they can ask you is the complexity also for dynamic programming, my dear friends. As I told you, the brute force method would be order 2 power n, my dear friends, but if you use dynamic programming, the time complexity would be theta n into C. C means capacity of the knapsack. So generally we are interested in, n items are there, C is the capacity. Some people write W for that, your wish, you can write anything. Maximum value of subset of n given items that can fit into a knapsack of capacity C. See, there is a difference between the knapsack problem which we do under greedy algorithm and this one. Because greedy method does not work for, the 0-1 knapsack problem cannot be solved using greedy method, my dear friends. So for that we have to use either this method or they use, what do you call that, branch करेंगे सर, क्वेश्चन प्रैक्टिस भी करेंगे like that. So that is about it. And of course this problems, I am not discussing greedy algorithm, because mainly greedy algorithm they can ask you problems in the examination that in the formulas I cannot discuss. So I just tell you what is the problem, what is the complexity, sir. So in Huffman coding problem, they will give you frequency, that is each character how many times it is occurring. Then they ask you an optimal way of representing each character as a binary code, okay, so that you can represent that in a better way, my dear friends. Okay, and for this, of course, we are going to use that tree method, binary Huffman tree also we call it. That method we are going to use, and the complexity would be theta n log. Here the main work would be sorting that values, the frequencies in a sorted order. That would be the main work, and that would be giving you complexity theta n log n, my dear friends. Then optimal merge pattern, what happens? We have n sorted files of length n, and an optimal way to pairwise merge these n sorted files into a single file. Of course, here also sorting would be playing very important role. So the complexity of this would be theta n log n, my dear friends. Because I am not discussing the problems, sir, because greedy algorithm, the main work would be solving the problems. So within this short time, I cannot discuss the entire story. So I am just discussing what is the problem, what is the complexity. Okay. Job sequencing problem, we are having every job associated with some deadline and associated with profit. If it is completed within the deadline, that profit will be occurred, otherwise that profit will not be given to that, my dear friends. Okay, and we assume that each job burst time is 1 and arrival time is 0. Means all the jobs are arrived at 0 time only, but the burst time we take it as 1, my dear friends. It's actually a simple variation of what you do in your CPU scheduling algorithms, my dear friends. So we need to find the optimal job sequence which gives you the best profit. Sometimes they ask you a question like which jobs cannot be performed, which jobs can be performed. This type of questions can be asked for this job sequencing problem. And of course here also the sorting these files according to their profits, okay, would be giving you the solution. So the time complexity would be sorting of those n files, my dear friends, according to their profits, and that would cost you theta and log n, my dear friends. In fractional knapsack problem, same story as we done earlier. N items will be there and we have a bag, or a knapsack means some bag of capacity. C is given and each items are there with some profit associated with them and some weight. So profit of ith item and weight of ith item is there, and how much fraction of that item you want to keep it in your box, my dear, or bag you are going to consider, my dear friends. So actually we are interested in what, sir? Suppose xith part of ith object if you taken, see full part if you take, pi is the profit. If you take only xi part, xi into pi is the profit. So you want to maximize this profit subjected to, because if you take xith part of ith object, how much weight is taken, sir? Xi into wi. So xi, x1 into w1, x2 into w2 and so on, xn into wn. This weight should not exceed the capacity of knapsack. So this is your knapsack problem, my dear friends. Thank you, Nicha. See, it's a quick way of reviewing all the formulas, my dear friends. I am just trying to do my best so that I can cover as many things as possible in a quick manner. Anyhow, this particular PDF will be available for you. Okay, you can just go through it. But I'll try to do problems. See, there are some topics because dynamic programming, what is important is explaining how you get the recurrence relation. But that cannot be done in a short while, sir, because entire dynamic programming only if you take it, that can be done in 3-4 hours. But now within a short time, I just want to review things faster, sir. Thank you. So we arrange them according to that profit per unit weight. Profit per unit weight, according to that would be the best strategy, my dear friends. Am I clear? Yes, Nishu Kumar, correct. And you understand many things, and why you worried about it, sir? You can do that. That's it. See, that is what is needed for algorithms course, my dear friends. Nothing much. For GATE point of view, it is sufficient, sir. But if you are preparing for other examinations, then you have to prepare accordingly, my dear friends. Okay, that's it. Of course, time complexity for this would be theta and log n, my dear friends. So the Huffman coding, optimal merge pattern, fractional knapsack problem, for everything it is theta and log n, my dear friends. Now about sorting methods, most of the people are waiting for this. So let me give you this and I'll conclude today's class, my dear friends. Okay, with sorting methods. Let me give you the sorting time complexities and their properties, like some people are asking, like whether it is in place, stable. So all those properties I'll try to put it in a tabular format for most popular sorting algorithms. See, the criteria for analysis of any sorting algorithm is the number of comparisons made, number of swaps made by that, and adaptive or not. Means adaptive in the sense, suppose if it is already sorted, it should consider that, no, because already sorted, it should do it faster. That is what you mean by adaptive nature. Means based on that type of your array or type of your input, it should perform better. So it takes advantage of existing order. That is what you call it as adaptive, my dear friend. Stable means the relative order of equal keys will be maintained. Okay, equal keys, original order will be maintained, my dear friends. Okay, see, you may be sorting based on a particular table entry will be there, no? Based on that you may be sorting, my dear friends. Suppose two values are equal, after sorting also their values will be meant. First one is first one, second one is second one, my dear friends. And the final is extra memory. Suppose if you take extra memory, then you call it as non in place. Suppose if you don't take extra memory taken is theta 1, then you call it as in place, my dear friends. See, what is an ideal sorting algorithm, my dear friends? An ideal sorting algorithm would have the following properties. It should be stable. Equal keys are not reordered. operates in place, that is order 1 extra space it should take. Worst case is theta n log n comparisons, key comparisons it should do, and only order n swaps it should do, and adaptive, and it speeds up order n when the data is nearly sorted or when there are very few unique keys, my dear friends. See, this is duplicate values हो सकता है. Yeah, that's what. If duplicate keys are there, their order is not changed. The duplicate order is not changed, my dear friends. Okay? Yeah. So there is no algorithm satisfies all these conditions, sir. See, we expect an algorithm or a sorting algorithm doing all these activities, but there is no sorting algorithm which can do all these activities, my dear friends. So based on your requirement, whatever is satisfied, that algorithm you are going to consider. Am I clear? Yeah, very good. See, there are two types of sorting methods. One is called comparison based one, the other one is index based sorting algorithms. See, comparison based algorithms cannot have a lower bound of complexity n log n, sir. You cannot perform better than n log n for them. Okay? But whereas index based sorting algorithm, you get, linear time sorting algorithms we call it, but for that we take extra space. Extra space is needed for this index based sorting algorithms, my dear friends. Selection sort, bubble sort, insertion sort, heap sort, merge sort, quick sort. Of course, there is something called tree sort. We are not discussing, sir. See, tree sort is simple, sir. We write binary search tree, then we write in order, then it is tree sort, sir. Nothing more than that. Index based are like counting sort, bucket sort, and radix sort are index based sorting algorithms. So these are the time complexities for these basic sorting algorithms. If you see best case, insertion sort is having best case theta n, bubble sort is also having best case theta n. Remaining all are having best case theta n log n or theta n square. Selection sort, if you observe, in all the cases it is having theta n square complexity only. Whereas bubble sort, best case is theta n, but worst and average cases are theta n square. Insertion sort is theta n. Actually, insertion sort works better when it is a sorted array, my dear friends. So for sorted arrays, insertion sort works better, my dear friends. Theta n is the complexity, but worst case or average case complexity for insertion sort is theta n square, my dear friends. Merge sort is same in all cases, even heap sort is same in all cases. Whereas quick sort, we already seen theta n log n for best case and average case. Worst case it is theta n square, my dear friends. As I told you, stable. Which one is stable, sir? Selection is not stable. Heap sort is not stable. Quick sort is not stable. Stable means what, sir? Already sorted array, insertion sort performs better, sir. Okay, like stable means what, sir? Stable means what, sir? Equal keys are reordered. Equal keys may be reordered using selection sort, heap sort, and quick sort. Of course, we can just manipulate these algorithms in such a way that the relative equal keys are not reordered, but is not the inbuilt in that particular algorithm, my difference. Yeah, quick sort, worst case for sorted. Quick sort performs worst case, gets worst case complexity for sorted arrays, my difference. And in place means except merge sort. Merge sort requires an additional space, my dear friends. Okay, remaining all are in place. Adaptive means selection is not adaptive, heap is not adaptive, merge and quick sort, they are not adaptive. Insertion sort is good adaptive algorithm because when it is sorted array, it performs better, my dear friends. Yeah, yes. Stable means duplicate elements order is preserved. Yes, Nitya. And of course, this time complexity for this, index based algorithms is given by, of course, they are saying linear time complexity by assuming k is that size of the extra array which you are going to take, my dear friends. So counting sort theta n plus k, bucket sort theta n plus k, because this radix sort actually uses the idea of counting sort only, d passes will be done. So it will be d times n plus k, my dear friends. Assuming d is constant and k is of order theta n, it would be theta n. Okay, generally k is considered as theta n and d is constant. So in such cases, all these are considered as theta n complexity, linear time complexity, by assuming that k is theta n and d is constant, my difference. Is the idea clear? Of course, if you consider stability, all are stable. No one, because the in place is the main problem. Index based algorithms, they are not in place. They require additional array for sorting your array, my dear friends. Adaptive, they do not sort, they are not adaptive, my dear friends. All these algorithms, index based algorithms, face these two natures. Of course they are stable, equal keys are ordered, because when you put those values in the other area, you can keep track of that. Stability can be maintained, my dear friends. But in place, no, because we require additional array, and adaptive, no. So these are the properties for all the sorting algorithms, my dear friends. You can just remember it, okay, for completeness. So except graph algorithms, I'll try to see that I'll mention some properties of graph algorithms later, sir. Remaining all are completed, my dear friends. So we already taken 2.5 hours long session. So graph algorithms also, you can just go through them. If possible, I'll try to provide that PDF also. Okay. So that's all for today. If you have any doubts, you can ask me. Otherwise, I'll call it a day. Hope you all remember the password also. Please note that password, my dear friends. Is the idea clear? Any doubts, please ask me, sir. Otherwise, we'll call it a day. It's a long session. Pretty long session. Lengthy. Long session. Hope you enjoyed the session. Okay. Most of the ideas we discussed prior. Graph PDF need to be shared, sir. That wasn't completed. I thought it's already a lengthy session, so graphs were not included in that. I'll try to include that graph formula little later, but I'll give you without any passwords. Thank you, Nitya. Very good. And I like the way you summarized what I was saying. Okay, so I think those who at least see the chat box will get a very good help by Nitya. Very good, Nitya. Super. And Nishu, very good. Vijayendar, very good, sir. And yeah. See, this would be done, sir, because if I take extra session, because remaining part, it's better if you solve the problems only than formula. See, because most of the BFS, DFS, their complexities are fixed. Okay, when it is adjacency list, order V plus E, and if it is adjacency matrix, it is order n square. Similarly, algorithms, if you take graph traversals or minimal spanning trees, if you take like Kruskal-log prims, order V log V will be the complexity. So there is not much to discuss. Only problems need to be discussed, sir. Mainly for remaining things, the problems need to be discussed, my dear friends. Okay. So this session is completed, sir. Algorithms, we call it a day, because the initial parts I discussed in a little more detail for what is required for you. I discussed that. The remaining parts mostly greedy, or see, most of the graph algorithms are greedy algorithms only. So they are we need to solve problems, because mostly in GATE exam also they ask you problem solving. So we require practice sessions for that. Yes, we'll do some practice sessions, sir. Maybe next month or this month somewhere. Okay, we'll plan that. Our team will plan those sessions. I'll come up with some practice sessions for both discrete mathematics as well as algorithms. I'll come up with some. Otherwise, you can take from any book, sir. Any standard book, you can just go through it, sir. Yeah, many books are available. Workbooks are available. You can take those questions. Previous year GATE questions first if you solve. That is minimum requirements. Yes. Good evening. Very good evening. And we are about to call the day, sir. Thank you for attending the session, and have a wonderful day, my friends. Good night. Good night to one and all. Yeah, Nishu. Thank you. Bye. Bye, sir. If you want to ask me anything, I'll wait. Otherwise, I'll call it a day, sir. Shall we call it a day? Yeah. Good night.